if I have time, yeah.
Oh, yeah, has Matt circulated today?
I'm sorry.
Have you circulated your notes for today, Matt?
I did not send a new email. The last email contained a link to the overleaf, which contained all of the current notes going forward. So no, I did not resend a separate PDF. Apologies for that.
No, that's fine. Thank you very much. It's been very helpful to go through while you're talking.
Okay, great. So welcome back for the third installment of what are we doing and how did we get here? We started off with a light speed recap of where field theory comes from, and last time we did a deep dive into what is the meaning of a gauge theory. I'm trying to spend exquisite time and detail getting us to the point that we can answer concretely what is QCD. And so I think now we are finally at that point that I can define concretely what it means to say that QCD is the non-abelian gauge theory of the SU3 gauge. And that's what I really want to tackle today, is explicitly using the machinery that we built to construct QCD and then look at what makes this particular gauge theory of SU3 and QCD distinct and different in fundamental ways compared to the familiar gauge theory of QCD. Okay, so last time we were discussing the ins and outs of a gauge theory. We started off by talking about approaches to interacting field theories, of which the primary workhorse is perturbation theory. I'm a big proponent of perturbation theory. It gets a bad rap sometimes because it might be a little bit vanilla, but it works perfectly well as a controlled systematic expansion. And that's a virtue that doesn't necessarily get enough praise. Not all expansions that you can do or not all approximation schemes are systematic. The classic counterexample that I like to give is density functional theory in condensed matter physics. Beautiful, excellent technique that's been very successfully applied to describe many materials, but it's not a controlled approximation. And the dirty little secret under the rug is, what is your error? What is your uncertainty on your favorite DFT calculation? DFT is great for what it's built for, but this is what perturbation theory is built for. Always having a controlled understanding of the next term in the series, the next error in your approximation. The other nice thing about perturbation theory is that if the change in your degrees of freedom is gradual enough, perturbation theory is self-correcting. It's capable of changing how it describes those degrees of freedom, even as you're using them to do perturbation theory. This is the technique known as resummation. We illustrated this last time with the idea of a large logarithm that can sometimes occur in your cross-section calculation. And if those logarithms show up in a systematic way, then you can write down where they come from and you can sum them all up. And completing that resummation basically defines a new degree of freedom, a new ground state, if you will, that you are now using as the basis for further perturbations. So those are things that perturbation theory does well, but perturbation theory is not the complete story, and that's important to always understand. If you adopt a perturbative point of view, if you do a calculation in perturbation theory, you will never see terms that do not have a series representation in the weak coupling limit. So you simply will not see essential singularities that lead to non-perturbative physics. Essential singularities that lead to non-perturbative physics are violent things. They typically come from something like a phase transition, or sometimes funny topological behavior where you have a protected quantity that's sort of either there or not there, and you can't gradually approach it in a smooth way. And then the other trick is, of course, that the perturbation series gets better for a while, but typically then it diverges again. That the perturbation series is formally divergent, and so even if you could calculate to next to next to next to next to next to leading order, it's not necessarily a good idea because that might not get you any closer to the truth. So with that sort of framework for what perturbation theory is and is not capable of answering, we started looking at the effect of the scalar modes in vector theories. I claimed that vector theories have a fundamental sickness to them. That sickness comes from essentially the presence of a scalar polarized mode. That scalar polarization was epsilon k scalar mu was I k mu over m for a massive particle. It's a polarization vector proportional to k mu, so that it's time-like for the massive vector field. So the potential existence of this mode is a threat to the ability to quantize the theory in any sensible way, because that scalar polarized mode leads to negative norm states that are inconsistent with the postulates of your Hilbert space. They sort of destroy the way that weight or probability is calculated in your theory. So the starting point for that discussion was the massive vector field. The massive vector field gives you the Procca equation of motion, which is just the Klein-Gordon equation that we're all familiar with, plus a constraint. That constraint, d mu a mu equals 0, is exactly the one that forbids the presence of those toxic scalar modes. So when dealing with an explicitly massive theory, you just have a constraint, and that constraint forbids the scalar modes. Gauge symmetry is the alternative that you use when you have a massless theory. A massless theory is not protected against the scalar modes by default. Sorry, massless vector. Massless vectors are not protected against scalars, against the scalar mode. So they're not protected against the scalar mode by default, but if you couple a massless vector to another particle or to another free theory with a particular kind of interaction, then the combination of those two can be arranged in such a way that those scalar modes become an unobservable symmetry transformation on the Lagrangian. So only when combined with a specific interaction vertex, that particular vertex is J mu A mu, where J mu is a conserved current, satisfying d mu J mu is equal to 0. Only when combined with that particular kind of vertex do you produce a Lagrangian that is invariant under those scalar modes. Does the scalar mode become an unphysical gauge symmetry? So I guess for me, the point that I took away from this discussion was that gauge symmetry is absolutely fundamental to the existence of the boson itself. That there is no photon without QED. There is no photon without this interaction with another field. The photon never exists in isolation. It cannot exist in isolation. It only exists as part of this conjunction of sources and fields together in a relationship with each other. Otherwise, the photon is not even well. Okay. The consequences of this, of course, are that one enlarges the symmetry. It means that you enlarge the global symmetry group. That global symmetry is the one that produced the conserved current in the first place. And coupling it together with this vector field generalizes the global symmetry to a local symmetry. Which basically allows you to sort of add and subtract scalar modes anywhere that you want, and even differently at different points in space-time. You can make a transformation of your gauge that is arbitrarily complex and arbitrarily different at point X versus point Y. This has a natural geometric interpretation. In terms of the curvature of the gauge direction. So sort of the language is the language of parallel transport, that I have an unequal comparison between point X and point Y because point X may transform differently than point Y. So in order to have a valid comparison of point X and point Y, I need to perform proper parallel transport of that phase information so that I can compensate for the different gauge transformations at different points of space. Okay, that was the major takeaway from the discussion last time. Maybe before I pause and ask for questions, let me share my screen quickly and point to a figure. When I give this discussion at the level of a colloquium, these are usually the words that I say instead of gauge theories and space-time plus gauge manifolds. I say when we're talking about QED that the governing principle is that electric charge is a scalar, that there is one and only one type of electric charge. It could be positive charge or negative charge, but there's only one direction, so to speak, associated with it. That is my way of trying to describe the gauge group U1, which is this rotation by a complex phase. Technically, it's a rotation matrix, but it's a 1-by-1 rotation matrix that isn't really rotating anything other than the phase of the complex number. So in this language, the gauge group of QED is a scalar transformation. Another way to say that is that it is an abelian theory. It's a commutative algebra. The thing that's going to change in a moment when we construct QCD is that there will be multiple different directions, so to speak, in which we can perform a gauge transformation. It looks a lot more like rotations in 3 dimensions, where I have multiple axes that I can rotate around, and those rotations don't commute with each other. It looks more like that than it does rotations in 2 dimensions, where I can rotate around the z-axis as many times as I want without changing it. So this is the critical difference that makes QCD a non-abelian gauge theory. It's essentially the same kind of gauge structure, but we take a matrix gauge group that allows rotations in different directions around different axes, so to speak. So before I dive into all of that for today, what questions do you have or comments or reflections on the discussion from last time? None? Okay, everybody's ready to get to QCD. Let's do it. Okay, so as I said before, now I think we are finally in a position to precisely define what I mean by quantum chromodynamics. QCD is the non-abelian gauge theory. Of fermions called quarks interacting with gauge bosons which are the gluons according to SU3 symmetry. And now I think we've discussed all of the framework to unpack what this means. So first thing, QCD is a gauge theory. That means it contains a massless vector boson, which is intimately related to a global symmetry that created a conserved current, and it extends that symmetry as a way of protecting against the scalar modes for the vector boson. So that gauge theory is necessary to ever define a gluon. The gluons are connected to the quarks due to the color symmetry of the internal degrees of freedom of the quarks. I specify how that interaction works by specifying what kind of algebra dictates that symmetry. Once I tell you what symmetry created the conserved current, then that symmetry is also the one which is the global symmetry that generates the gluons. That symmetry, SU3, is a matrix theory. This is the group of 3 by 3 unitary matrices with determinant equals +1. That matrix group is very different from the scalar group U1 we had before, and that critical difference is that that matrix group is non-abelian. It is non-commutative. So the exercise in going from gauge theory of QED to gauge theory of QCD is a lot like going from the properties of rotations in 2 dimensions, where all of the rotations commute no matter how many times you rotate about the z-axis, and going to 3 dimensions, where now I have multiple independent axes of rotation issues. Okay, so last time we set up the procedure. The procedure is to start with a free Lagrangian and identify the global symmetry that you're going to gauge. So before a gluon ever enters the picture, first I have the quarks. First I have free non-interacting quarks, which are described by the free Dirac Lagrangian. The free Dirac Lagrangian was psi bar I/d/ minus m psi. This was my starting point for getting QED. The only difference if I want to get quantum chromodynamics is now I assume that there is an internal degree of freedom. That internal degree of freedom is the one that we'll call color, and it basically means that my psi has an extra label in it, psi I, where I in this color notation could be red or blue or green. These are my 3 choices of color. This is referred to as the fundamental representation, or the defining representation. So if I have a non-interacting theory, then the color doesn't do anything. It's just sitting there as an extra passive quantum number. And I have a Lagrangian that adds up the red quarks, and a Lagrangian for the blue quarks, and a Lagrangian for the green quarks, and I add them all up together. But the key is that this Lagrangian, when I sum over I equals red, blue, and green, that Lagrangian doesn't care whether your particular quark was red or blue or green. So the new symmetry comes from the ability to rotate among these different colors, to switch between a red quark and a blue quark, which this Lagrangian doesn't care about. But that introduces now a matrix type of rotation, more than just the complex space. So this is the global transformation of the for rotations among the colors. The transformation that I make is psi prime with color I at space-time point x is obtained from my original psi at space-time point x, but potentially from a different color. And then I turn that original color into the final color by this rotation matrix. So I have e to the I phi a t a ij component. This object is a unitary matrix, so you might write this as uij. The ij indices here are the fundamental colors. So just as if these were Cartesian axes x, y, z, this tells me the element of the matrix that describes the rotation of, let's say, an initially red quark to get a blue quark. That would be the blue comma red entry of that matrix. And this matrix is nothing weird. This is just the usual form like a rotation matrix. Compare it with the rotation matrix in quantum mechanics, e to the minus I over h bar j dot theta. Here, this dot product shows up in the form of this sum over all generators, over all of the different axes of rotation. So here, the TAs are the generators of SU3. And then these quantities here, phi, these are the angles of rotation. Angles of rotation about each axis. So I will refer to the color index A as specifying the axis of color rotation. There are many different axes to choose from. The IJ tells you the element, which fundamental color got rotated into which other fundamental color as a result of rotating about a particular axis. In general, the thing upstairs in the exponent is a dot product. So the way that you choose a particular axis is I pick that vector to be a magnitude and a chosen direction. So here it's written as a sum phi A TA, but these phi A's are arbitrary. You can choose to rotate about any combination of axes you want.
Sorry, I have a question.
Yes, please.
Is there any specific reason why we restrict ourselves to SU3 matrices when considering a non-abelian gauge symmetry? Because to my mind, the natural generalization of a U1 symmetry would be a U3 symmetry.
Yes.
So is there any?
So excellent question. So I was going to come to this a little bit later, but maybe let me comment on this now. So two pieces of, let's say, experimental input that help us determine what the ultimate correct gauge group is. One of those comes from hadron spectroscopy. The fact that when you look at all of the possible hadrons that you can make in nature, some of them look familiar, like the proton. The proton in its quark model picture is 2 up quarks and a down. The one that gives us a real hint about what the gauge group needs to be is the omega minus baryon. The omega minus is a particularly weird particle because it's made up of 3 strange quarks. And all 3 strange quarks have the same spin configuration in a quark model picture, leading to this 3-halves spin baryon. The point is that the omega minus should not be able to exist unless I have a quantum number like color that comes in 3 different varieties, because otherwise I cannot satisfy the Pauli exclusion principle for a ground state made up of 3 strange quarks in an S-wave state. So the observation of the omega minus baryon, the successful prediction of it within the quark model, its mass, its charge, its spin, the fact that it works strongly suggests that I must have, in order to satisfy the exclusion principle, a new quantum number that comes in 3 varieties. So that's, I think, part of how we know the number should be 3 and not 7. But you raise a very good question about why it should be SU3 and not U3 or something else. This, I'm very happy to show you a figure that I was shown by your own Will Horowitz. I learned this in our discussions, and that was very nice. So Will, apologies for throwing your own figure back in your face. This is a really nice experimental plot that Will brought to my attention that shows exactly the comparison you asked experimentally based on the measured production rate of 3 jet events. So the thing about QCD, as we'll get to in a minute, is this self-interaction vertex of the gluons. So that it's possible to have not only 2-to-2 scattering, but also 2-to-3, where my gluon can branch, and I get this distinctive 3-jet signature. But depending on which gauge group I have, I get different rates for how much I get of those 3-jet events. So if I understand the plot correctly, this is a demonstration as a function of the different color factors of many different gauge groups, the relative so it's based on a measurement of the 3-jet production and how consistent or inconsistent it is with the different color factors. Let me put it that way. So this was a particular measurement from Aleph at LEP that shows something that is very nicely consistent with SU3. SU3 must be the star. Yeah, QCD equals SU3 is the star here. as opposed to something like U1 or SO2 or SO3. All of these other gauge groups fall in different locations. So we need experimental evidence to help indicate what the correct gauge group should be. Some of that comes in the form of spectroscopy, some of it comes in the form of collider measurements, but I think the different gauge groups make different predictions for the rates and strengths of these different effects. So by pinning those down experimentally, we can get a good handle on what that correct underlying theory is. Very good question. Does that answer?
Yes, yes. Thank you very much.
Excellent. Great.
Well, I'd say almost. It doesn't. Right, what you saw there were a bunch of groups.
Should I put it back up, Herbert?
Not necessarily. I mean, you saw a bunch of groups, right? And they all differ in the number of degrees of freedom that you have that goes in there. So this is what you see on the axis. What's not on there is a U3. It's not on, right? So that has not, in this way, this doesn't explicitly delete the S. But there is an issue, of course, right? U3 would have one more generator. Right? Has one more degree of freedom, essentially. It's not A, right? It would be n squared instead of n squared, minus 1. And so where does that go? Well, it's very much, in terms of mathematics, it very much looks like a photon. It's the aphelion bit. And so this is essentially double counting. That's the way I think about it. You have already a degree of freedom of this sort in the thing, and you see it as a photon.
I mean, of course, there are U1s in the standard model, but with different charges.
With
so
different
you could have
charges.
several U1s, of course.
You could have several U1s,
So
but
the
then you
U1
would
we
sneak
have
to.
doesn't look like a
Yeah.
QCD U1.
Yeah, it doesn't look like a QCD.
Doesn't have the right coupling. It doesn't have the right
Absolutely, absolutely. Yeah.
So could that extra one be a QCD photon that's colorless?
Well, in the sense.
I don't know if it exists in nature or not, but it definitely exists in the mathematics, and that's one of the real nice advantages of the large NC limit.
So you would have one too many, right? You would have one more thing that talks to the color components.
Wouldn't that be? I mean, if it was a QCD U1, it would kind of be a U1 that would couple the color singlet particles.
Yes,
So
precisely.
you would have extremely strong interactions between protons and neutrons.
Yes.
Mediated
That's-
by
yeah.
this particle with kind of a QCD coupling. And we don't see such strong interactions.
Yes. That's not bad.
Very good.
Kind of U1, it would be the trace U1. So I think it would couple the color neutral particles to U1.
Good.
Okay, shall I continue?
electric thing also doesn't couple to it. I don't think it would couple to color neutral, even if it's a U1.
Sorry, I can't tell if the discussion is continuing or if I should move on.
We should do this. We should take this offline. This probably needs a little thinking.
Yeah, we could-
Very good questions. So something a little more basic in terms of, again, counting the number of degrees of freedom. One question that you always get when you show QCD for the first time is, how many gluons are there and why aren't there 9? It seems like there should be 9 because I have 3 initial colors, 3 final colors, so the number of elements in this matrix is 9. It seems like I should have 9 different C's or different combinations to choose from between initial and final state colors. The number would be 9, as we just said, if the group was U3. But since the group is SU3, that S imposes a constraint condition, namely the condition that the determinant of this unitary matrix is 1. So that constraint condition exactly removes the contribution of this QCD photon that was just being discussed. And that drops that 9 down to 8, which is the number of generators for SU. Those particular generators are the Gell-Mann matrices, up to a factor of 2. So the generators of SU3TA are conventionally written as 1/2 lambda A, where lambda A are the Gell-Mann matrices. And as we just discussed, A is an index which goes 1, 2, up to 8, as opposed to the IJs, which are fundamental indices, which go from 1 to 2 to 3 to be red, blue, and green. Those would be the IJ elements of these matrices. There's nothing strange or magical about the Gell-Mann matrices. They're all written out in my notes, just to show you a few of them. The first Gell-Mann matrix is this one, which should look familiar. The second Gell-Mann matrix is this one. The third Gell-Mann matrix is this one, and so on. Other Gell-Mann matrices have a similar form, but then they put the ones or the I's in different rows and columns to mix things together. These particular Gell-Mann matrices should look extremely familiar, specifically that sector, and that sector. What are those first 2x2 blocks of these matrices?
Rotations.
Yes, they're specifically rotations of 2x2 rotation matrices that act on spins, which are called what?
Pauli matrices.
The Pauli matrices, exactly. This one is the Pauli matrix sigma x. This is precisely the Pauli matrix sigma y, and that's precisely the Pauli matrix sigma z. You'll notice that lambda 4, 5, and 6 are, as 7 as well, are just different variations of essentially the Pauli matrices, just with these patterns repeated in different elements. The only one which is sort of special and unique is lambda 8, which is diagonal but traceless. 1, 1, nice. Notice, by the way, that all of these generators are traceless. Trace of the TAs are equal to 0. That follows from the requirement that the determinant of the matrix has to be equal to 1. Since the unitary matrix is the exponential of the generators, if this determinant is 1, then that trace needs to be 0. Okay, so those are the ingredients, the generators that are responsible for the basic building blocks of SU3. This is, as I said, the fundamental representation which is associated with quarks. So that 3x3 fundamental representation, where your TAs are 1/2 lambda A's. This is the fundamental representation associated with the quarks. To construct the representation of the gluons, we need the structure constants. The structure constants come from the commutator algebra of these matrices. If I take the commutator of 2 of the generators TA and, a different one, TB, my answer is a linear combination of those same generators, TC, with coefficients FABC, which are manifestly anti-symmetric among all 3, and a conventional factor of pi. So once I define these matrices, I can exactly calculate their structure constants. The values themselves are tabulated in the notes. I don't know if there's anything particularly illuminating for me to say about showing you the values. The thing that's special about them is their anti-symmetry. They're anti-symmetric in all of the indices. So FABC is negative FBCA, and it's also negative FACB. The structure constants, because of how they're related to the commutator, actually also satisfy the properties of the group. So the FABCs themselves are actually another 8-dimensional representation of SU. So if I define something that looks like an 8x8 matrix, I'll call it capital TA with indices BC. If I define this to be minus I times the structure constant FABC, then this also satisfies the same algebra condition. If I calculate the commutator of these matrices, TA and TB, I also get IFABC, the same FABCs as before, now with capital TC. So this is exactly the same algebra, but different representations. The fundamental representation is the 3x3 representation. This one is the 8x8 representation. This is called the adjoint representation. And it's worth noting, the reason that this happens, the reason that you get this identity is through the Jacobi identity. The Jacobi identity tells you that if I take all cyclic combinations of commutators, so CA with TB and TC, plus all possible cyclic permutations. TC, TA, plus TC, TA, TB, add it all up and I get 0. If I take this expression and solve it for FABC, I can basically plug it in over here. You can plug in for these commutators in terms of FABC, and the result gives you exactly this. So the algebra works out that the generators have exactly the same properties as the group itself. And so that 8x8 adjoint representation is the representation of the gluons. So your gluon might start in A mu A from A equals 1 to A equals 8, and this is my transformed gluon field. I have 8 possible colors to begin with, and now I can have a unitary adjoint transformation that's going to change the color of the gluon here to the color of the gluon there. This is just schematic, the actual gauge transformation, which we'll write down in a minute, is more complicated. So that was to try to explain what the idea is of fundamental representation and adjoint representation. These are two different representations of the same algebra. They have exactly the same properties, but they live in different dimensional spaces. The 3-dimensional color space for the quarks, the 8-dimensional color space for the gluon. I think at this point, a comparison to SU2 is helpful, since we already saw the Pauli matrices showing up as the building blocks of the Gelmani matrices. So for clarity, for SU2, the transformations looks the same. I would have psi prime I equals e to the I beta A Ta psi j, where this is the ij element of my rotation matrix. For SU2, the generators are the Pauli matrix, sigma A. And in exactly the same way, we know that there's a difference between the dimension of the Pauli matrix and the number of such Pauli matrices there are. So each Pauli matrix, like sigma x, is a 2x2 matrix. That's because the fundamental representation describes a system that has 2 degrees of freedom, right? A spin up or a spin down, that's a 2-dimensional space. So you have a 2-dimensional matrix acting on that space. But even though I'm acting on a 2-dimensional fundamental representation, there are 3 of the Pauli matrices, sigma x, sigma y, sigma z. The number of those generators is 2 squared minus 1, right? It's 2 initial spins times 2 final spins minus 1 to subtract the identity matrix. So this idea of fundamental and adjoint is not so alien to us. It all goes back to the Pauli matrices of 2x2 Pauli matrices because the spins come in 2 degrees of freedom. But the gluon, so to speak, the number of axes of rotation that you have is larger. You've got many ways to rotate among those 2 spins. Okay. Any questions at this stage before I talk about large NC?
maybe a quick question. So if we think about protons, neutrons as a canonical SU2.
Sorry, I'm having a real hard time hearing. Can you speak up?
Yeah, sorry. So I'm just trying to think about your comparison to SU2. So when we do rotations, we don't really care about the adjoint representation. So I guess I'm trying to think a little bit about a quantum field theory analogous to QCD, but using SU2 instead of SU3. So I'm thinking about, I guess, the original Yang-Mills theory of protons, neutrons as the SU2, and then I guess my gauge bosons, I would have, how many of them? I guess I'd have 3 of them, right? And what are those, what's the interpretation of the gauge bosons in that theory? Like, do they correspond to anything approximately that we see?
Well, I mean, if I understand the question and the dictionary correctly, then the gauge theory of SU2 is the weak force, and that would mean that there should be 3 bosons, which there are, which correspond loosely to the W plus W minus and Z. There was the first part. The question about the higher dimensional representations of the Pauli matrices. That's also familiar to us. That's the spin 1 representation of SU2. So I can write down the 3 by 3 spin 1 matrices, and that's the adjoint representation.
Yeah, so I'm definitely, yeah, okay, sure. WZ for SU2 is the fundamental theory, but the original idea of SU2 as a gauge theory was in terms of protons, neutrons, right?
Yeah, so ions are the adjoint representation.
Okay.
But now we're talking chiral, right? This is and it's not gauged in nature.
Yeah, it's I don't know if yes, sorry. But of course, I mean, weak interactors are gauged. So if you think of, I mean, principally, think of ions interacting with W bosons. Of course, we know that ions are not fundamental. You could think of ions as an adjoint representation matter interacts with W.
I just have a quick question.
Yes, please.
So the idea that we're doing here is we're starting off with the assumption that, okay, we're going to have some fermions that have this thing called color.
Yep.
We're just going to call it color. And we describe how color transforms.
Yes.
Then from that, we're going to build up QCD. And that's all we really need.
Yes.
Cool. That's
Exactly. That's what's so profound about it to me, is that the only idea that you need is SU3. And as soon as you have SU3, you can write down QCD unambiguously. So yeah, that's what we're about to do now. Excellent. We'll do it in 1 second after a comment about large NC. Okay, large NC very quickly. We've talked now about a couple of different specific cases. QCD that we really care about is SU3. We just did a comparison to the simpler group SU2. You can see that not much changes in the structure of the argument if I go from 2 to 3 to N. So the general case is often written as SUNC. NC is the number of colors. Of course, number of colors is a vague statement. Really, I mean the number of fundamental colors. Or the number of quark colors if you want to put a physical term on it. Not that much changes about the nature of the theory if I just go to arbitrary n. In general, I will have NC number of possible internal degrees of freedom of the quarks, and the number of adjoint colors is going to be NC squared minus 1. And one can calculate all of the color factors that come out for arbitrary NC. Not really much is harder about doing, trace of TA, TB for SUNC compared to SU3 or SU2. So first comment is it doesn't cost you very much if you want to work for arbitrary NC and then specify NC equals 3 at the end of the day. But the second comment is that it's also advantageous to take an unphysical limit, so to speak, in which the group theory simplifies enormously. So that very clever limit is the 12th large NC limit. The premise of the large NC limit is that you're working in the weak coupling limit where alpha strong is going to 0. But simultaneously, you're taking the number of colors to infinity. So it is still a weak coupling description with many colors. And you take this combination of limits in the specific way such that the product alpha S times NC is constant and small. All of this is sort of technical details. For our purposes, the important thing is that we're taking NC to infinity. And if NC goes to infinity, I simplify parts of this algebra. In particular, if NC is going to infinity, compared to infinity squared, that one doesn't look like it's doing very much. The short answer is that if I have SUNC going to infinity, and I compare it with UNC going to infinity, these things are only different by one little generator. And one little generator, the photon or the identity matrix compared to infinity number of other ones, is irrelevant. So essentially, what's happening is that in the limit NC going to infinity, I can forget the S. I can forget that constraint condition. And that simplifies the properties of the color flow quite significantly. I think the clearest illustration of this is in the Sievert identity. The Sievert identity is just a mathematical identity in terms of a product of the generators. If I have two generators with arbitrary indices, I'll write them like this: I, J, K, L. But the A is repeated and summed over. If I sum over that, the Sievert identity for arbitrary NC gives me 1/2 delta IL delta JK minus 1/2 NC delta IJ delta KL. I'm not sure how intelligible it is in terms of indices like this. Often people draw a diagram to go along with it to illustrate the color flow. So this is supposed to represent something that you would get if I have, let's say, fundamental color J coming in, fundamental color I going out, and an adjoint color A being exchanged. On the other side, I have fundamental color K coming out and fundamental color L coming in. This is the left-hand side of this equation. The right-hand side says there's two terms. The first one has I goes to L, that's this, and J goes to K, that's this. And the second term is -1/2NC times something that sends the color back in its original direction from J to I and K to L. This is the Sievert identity. It's a really great property, very useful for calculating traces and things that show up in QCD. But you see that there's two different terms with two different color structures that show up. And for finite NC, I have both of them. And every time I have a diagram with a glue on, I repeat this identity over and over and over again, and it generates lots and lots of terms. But if NC is large, NC is going to infinity, then this second term, the one that's being subtracted off, doesn't matter. It's explicitly suppressed as NC goes to infinity. So what happens is I completely kill off this second complicated color flow, and I have only the first one, which means it looks like this gluon that was propagating with colors JI on this side, KL on that side. It just gets replaced by a straight line. It looks like my gluon is equivalent to a quark and an anti-quark sitting on top of each other, at least as far as color is concerned. This is not a statement about any other physics. It's just the representation of the color flow. That in large NC, where I don't have to worry about the constraint condition that guarantees that I have determinant 1 and therefore no photon. That becomes unimportant, and I get just a simple planar flow of color. This is the big simplification that comes from the large NC limit. So large NC is often simpler to solve than finite NC or NC equals 3 because it simplifies the color algebra for you in a controlled way. So large NC first and foremost simplifies color algebra greatly. And that simplification is essentially due to going from SUN to UN, where that second piece for SUN becomes irrelevant and you can throw it away. This also, as we indicated before, it ignores quarks compared to gluons. The reason is because there are only NC colors of the quarks, but there are NC squared minus 1, which is approximately NC squared number of gluons. So if I take my theory in the large NC limit, it's a theory where the quarks are irrelevant. Maybe they give you initial conditions and then you forget about them. But all of the interesting dynamics is glue upon glue upon glue, which is why this is a very powerful description for getting a gluon saturation, just from what they try to get to. Okay, that's the trick of large NC. I can't pass up the opportunity to comment on the accuracy of large NC. If I want to do a real-life calculation where NC equals 3, and I use an approximation where I work in large NC, that means that I've dropped terms that are suppressed by powers of 1 over NC. So if I'm doing this series expansion and NC equals 3, then I'm sort of doing an expansion in powers of a third. If I naively think about it, I would say, well, my first order correction is 1 over NC, but most cross sections don't have a correction at this order. Most cross sections have a correction at order 1 over NC squared. And if it's 1 over NC squared, then I would expect my error to be about 1 over 9, which is about a 10% uncertainty from approximating my problem by the large NC limit. My naive estimate would say I should expect about 10% accuracy. But what's remarkable is that most of the quantities related to small x physics, high energy QCD, gluon saturation, for most of that, large NC works even better than this, better than one necessarily has the right to expect a priori. I believe the correct statement is that for things like the BFKL intercept and quantities like that, that the accuracy is actually another order of magnitude better than this. It's more like 1%. But if you have questions, you should absolutely ask Thomas, who did some of the original work that established the accuracy of this expansion. Okay, any questions before we move on to gauging the QCD Lagrangian?
Sure. So I may have missed the argument why the error is only up to order 1 over NC squared. Because to my mind, the error should be over 1 over NC.
It depends on the quantity that you're looking at. Some processes have corrections of order 1 over NC, but I think just in my experience, most of the time in cross sections, it ends up being 1 over NC squared. Although I think if I imagine asymmetries or something, you can come up with funny scenarios that are 1 over NC. Would you say that's fair, guys?
I think one way to see it is that somehow you will be comparing NC squared minus 1 to NC squared. And there the difference is 1 over NC squared. And typically,
oh, I like that. Yeah. Gotcha. So you're saying this, that you're effectively replacing something that should be 1 over NC squared minus 1 with something 1 over NC squared. So your error is of order 1 over NC squared.
And now, of course, there are things that you get into trouble with, right? If you think about building mesons or baryons out of this stuff, mesons are good. Mesons are good because you have so 3 you have quark and antiquark pairs. To make baryons, the number of quarks that you would have in a valence quark model would scale up with NC, and that makes these guys humongously heavy, right? And they decouple from the theory. So there are certain questions you can ask and certain questions that you cannot easily ask, at least if you put the quarks into the fundamental representation. There are other funny tricks that people have tried, but that's calculationally monstrous.
Yeah, that's a good point that I want to just repeat, that NC also shows up in things like how you make a baryon. Because a baryon needs to be something that is color neutral, and therefore it has NC number of quarks all in a different color state. So in our real life, NC is 3 and the proton quark content is UUD. If I change NC to 4, then now my proton should have 4 quarks in it, not 3. And if NC goes to infinity, my proton should have infinity number of quarks. So yes, point well taken, Aaron. Thank you. Okay. So now let's power through the technical part. So now we know exactly what we want to do. We want to start with the free Dirac Lagrangian with a multi-component description for the wave function. Sorry, for the Dirac field. So I have psi bar I ID slash minus M psi I. This possesses, as we said, invariance under global U1 transformation. Sorry, global SU3 or even SUNC transformation. Psi prime j is UJI psi I, where U is e to the I phi a ta. This leads to a conserved current. So if I do the usual exercise from Noether's theorem, I get 0 for the variation in the Lagrangian because it's a symmetry, and that variation comes from variation in the Lagrangian with respect to psi times the change in psi plus the variation in psi bar times the change in the Lagrangian plus the change in the gradients. So for our particular Lagrangian, let's see, this is 0. I have something that depends on, yes. So one of these terms is 0, the other one I substitute from the equation of motion, and I write this as d mu of variation of the Lagrangian with respect to d mu psi I, delta psi I, and then the two terms together combine into a total derivative. So I have a derivative of the first term, derivative of the second term, add them together, and by product rule, this gives me 0 equals the total divergence of variation of Lagrangian with respect to d mu psi I times delta psi I. So this is my conserved current J mu. I just need to identify what it is. If I calculate this derivative from the Lagrangian, I take the infinitesimal transformation. What I get is up to 8 different conserved currents for any of the 8 different directions of the gauge rotation. And it's of the form psi bar I gamma mu ta ij psi j. So this has very much the same form as the particle number current from E and M, from QED, psi bar gamma psi. That's the vector structure. The color structure is a rotation. Notice that I have the rotation matrix TA inserted in between the different color states of the quarks. So this interaction describes a current of quarks that are moving with vector direction mu with well-defined color axis A that is constantly rotating those quarks. So this is A equals 1 up to 8 different conserved currents. As shown here, they separately satisfy d mu j mu A equals 0 for all A. And that's the basis that we use to introduce the gluon field and gauge the Lagrangian. So now I insert the vertex with the minimal coupling form. So this is what I'll call the gauged Lagrangian. That's my psi bar I, ID slash minus M psi I. Now with the J mu A mu vertex. So I have minus coupling constant G. I think for this convention I choose plus G. Psi bar I, gamma mu, T A I J psi J times A mu A. Yes. So now I have A equals 1 up to 8 vector fields. These are my 8 gluons. And then I can combine these two structures together. This gamma mu is also here in the D slash. The D slash is gamma mu derivative mu. So I can combine those two things together. This is psi bar I. I have, let's see, I gamma mu times d mu minus IG A mu A T A minus M psi I, no, psi J. I guess if I'm putting the indices on here, this is TAIJ, and then this is the identity matrix, delta IJ. And I guess I need a delta IJ here if I'm putting the color indices explicitly. So this is what defines my covariant derivative. The effect of adding in this minimally coupled vertex basically just replace d mu goes to capital D mu, which is little d mu minus IG A mu A T A. So this is our gauge covariant derivative for QCD. That now gives us the form of the current, the form of the interaction vertex. There's only one thing we're missing. The thing that we're missing is the free field component, the kinetic energy, so to speak, of the gluons. So the last part is the gluon kinetic term. It should be something like minus 1/4 F mu nu F mu nu. That was what it was in QED. And we said that I can get my F mu nu by building it out of a commutator of covariant derivatives. So I can calculate the commutator of the covariant derivative d mu and d mu. So this is the commutator of partial mu minus IG A mu A T A with partial nu minus IG A mu B T B. And then I just expand the brackets. The commutator of the partial derivatives is 0. The commutator of one partial derivative with the field gives me the term where the derivative acts on the field itself. And then the last one gives me a commutator of the two generators. So I get minus IG d mu A mu B T B plus IG d mu A mu A T A minus G squared A mu A mu B commutator of TA with TB. And then I plug in for the commutator in terms of the structure constants FABC. And I find that my commutator of covariant derivatives d mu d nu is minus IG times the quantity d mu a nu c minus d nu a nu c plus g f a b c a nu a nu b times tc. So this object is the one that generalizes the field strength tensor for the non-abelian case. This contains the old F mu nu that we had for QED, just the generalized four-dimensional curl. But now we also have an extra piece which gets added to this that comes specifically from the commutator of the matrices. So that non-abelian nature, the fact that I have a commutator, means that FABC makes a direct contribution here. So this is a new non-abelian term. So this is what serves as the basis to define F mu nu of color, let's say A, is d mu a nu a minus d nu a mu a plus g f a b c a nu b a nu c. So this is the QCD field strength tensor. And this was the last necessary ingredient to construct the full QCD Lagrangian. So the full QCD Lagrangian is the free direct part, psi bar I d slash minus m psi. We have the minimal coupling vertex plus g psi bar I gamma mu ta ij psi j, and the free kinetic energy minus 1/4 F mu nu a F mu nu a. And this gives us the whole thing. This, of course, as we already showed, can be combined together in terms of a covariant derivative. Psi bar I capital D slash minus M psi j now. This is an IJ matrix. There's an IJ here. Okay, so we've used the technology that we developed last time to construct the QCD Lagrangian. Before we dive into the implications of that, I want to check the properties of the gauge transformations. How are we doing on time? 15 minutes, okay. Right, I want to derive the form of the gauge transformation on A mu. So we found the covariant derivative. We had d mu was partial mu minus ig a mu a ta. And I want to use this to find the transformation of the vector field A under my gauge transformation. One simple way to do that is from the definition of the covariant derivative as parallel transform. So the covariant derivative is supposed to have a transformation which is local. The effect of that d mu is that it cancels the non-locality of the gauge transformation and just gives me the unitary matrix thing on the covariant derivative itself. So this was what we showed last time, that the definition of the covariant derivative sort of means that it commutes with that rotation. That the effect should just be that that overall gauge transformation comes out from the outside. So I'm going to use this requirement to find out what the new transformation is on the gauge field A. So the transformed version of the covariant derivative is d mu minus ig a mu a prime, whatever a mu a is after it transformed, ta. Acting on psi, psi is the transformed, acting on psi prime, the transformed psi, which is u times psi. On the right side, I'm supposed to get back u times d mu minus ig a mu a ta psi. So I just want to take this expression and solve it for A prime or equivalent. So, okay, let's open up the parentheses. On the left-hand side, the first term that I get is d mu of u times psi. Second term is u times d mu of psi. Third term is minus ig a mu prime a ta u psi. On the right-hand side, I have u times d mu psi minus ig a mu a and then u ta psi. Remember that TA, the generator TA, is a color matrix. That's getting multiplied along with this transformation. So this u sits to the left of the TA. Some things cancel in my expressions. Here I have u d mu psi on the left. I also have u d mu psi on the right. And so now I can solve this in terms of, let's say, A prime, or equivalently solve it for A. So one way of expressing what this transformation is telling me is to rearrange this equation and then I get A mu A TA equals A mu A prime U dagger CAU plus I over G U dagger D mu U. This maybe is not a super intelligible way of writing the transformation, although it is complete. An equivalent way of writing it, if I open this up and solve it for A mu, is to get A mu prime equals A mu plus 1 over G D mu phi A plus FABC A mu B phi C. So this is the point that I wanted to make, which is that the gauge transformation in QCD looks different. The gauge transformation in QED was A prime equals A plus a scalar mode. And we showed that the scalar mode can get absorbed into a harmless redefinition of the field. Here it's not so trivial. Here the gauge transformation, or let me put it this way, here adding in a scalar mode is partly equivalent to redefining the fields, but it also introduces a vertex. So I can eliminate the scalar mode and hide it into a redefinition of the fields at the cost of adding an interaction term in the process. So this transformation is not so passive, you put it that way. It's not just adding a scalar mode and you get rid of it. It's now coupled to an interaction, which is entirely related to the fact that the free kinetic energy is not gauge invariant. So if I take that transformation for A, it's much easier to express the transformation in terms of F mu nu. The transformation in terms of F mu nu is F prime mu nu A equals U F mu nu A U dagger. And I think I've got my primes in weird places here, so don't quote me on which one is U versus U dagger. The point here is that the field strength tensor is not gauge invariant. F mu nu A is not gauge invariant.
You should leave off the A. You should treat it as a matrix if you write it the way you write. F prime. Yep. Yep.
Yes. So yes, everything is scalar. Yes, thank you.
And you might want to say that on the left half of left half of your board, when you express things in phi, this is expanding U out in powers of phi. This is the
Yeah, that's right. So the connection here is that U equals e to the I phi A T A. So I just made that substitution going from here to here.
And you expand it to lowest order in phi.
Yeah, this is for an infinitesimal transformation, I guess. Is it? No, I don't think so.
Yeah, it is.
Cancel the overall phase rotations, but okay, technical detail. The point physically that I'm trying to make here is about the invariance or lack thereof of the free kinetic energy. So there's various ways to see this. So one of these is to say that the field strength tensor, which has the QCD analog of the electric and magnetic fields. Sometimes people call them the chromoelectric and chromomagnetic fields. These things have a particular color index in them. So you can talk about the red minus blue color field, chromoelectric field. And you can talk about that for different colors. The fact that you can have them for different color directions is what makes it non-gauge invariant. So you can have something which is gauge invariant if I sum over all of these things. F mu nu A, F mu nu A, summed over all of these colors is gauge invariant. But these things separately are not. That's one important difference between QED and QCD. That in QED, the electric field is an observable. In QCD, the electric field of given color is not observable. Another consequence of this is that the free kinetic energy, if I wanted to make a free non-interacting gluon, I would have that minus 1/4 d mu a nu minus d mu a nu . I would have just this part without the extra FADC term. The flip side is that this piece, the non-interacting part of the gluon propagator, the gluon kinetic energy, this piece is not gauge invariant. So that's another way of showing that if you try to have a free gluon propagating through space, minding its own business, it doesn't work. This is not protected against the scalar mode. Only if you couple it to something like the quarks do you have the ability to absorb that scalar mode into the redefinition of the fields. Okay, implications.
I just have a question.
Yes, please.
So are we saying that so things can't be observable if they're not gauge invariant?
Correct.
Okay, and and all this is about making sure that we can get rid of the scalar mode, and you can only get rid of the scalar mode if it's gauge invariant.
That's right. So the scalar mode is the gauge transformation, so to speak. And so getting rid of the scalar mode means your Lagrangian has to be invariant under gauge transformations. So as long as you maintain invariance under gauge transformations, you are guaranteed to be safe from the scalar.
And anything that isn't, we call unphysical.
Correct. So anything that is not gauge invariant may have unphysical scalar modes running around in it, and only after you you cancel them out, only after you look at an observable that is insensitive to those scalar modes do you have something physical, something that you could really observe and that would be unaffected by the.
Okay, thank you.
Okay, so we wrote down the QCD Lagrangian in its, let's say, more compact. To actually use it for something, we need to expand it out into its full glory. So we said the Lagrangian for QCD can be written as psi bar I v slash minus m psi minus 1/4 f mu nu a f mu nu a. But if I open this thing up in terms of all of its full structure, I get the free terms psi bar I v slash minus m psi. I can pick out just the free part of this gluon kinetic energy, even though the whole thing is there. Those are sort of the free or non-interacting pieces, and then I have the vertices. One of the vertices is here in the covariant derivative. That's the minimal coupling that we used from the start. So that gives me back the plus G psi bar gamma mu Ta psi a mu a. The other piece is the gluonic self-interactions come here from the F mu nu squared. Remember that each F mu nu has this free part plus F A B C A B A C. So there's two gluon fields and a structure constant that shows up. And that happens in this factor and also in that factor. So when I distribute these things out, I get two types of gluonic interactions. A cross term that has 3 gluon fields from one of these terms and one of these, and a 4 gluon term that has both of those FABC type. So those extra pieces are minus GFABC A mu B A mu C times the derivative D mu A mu A. Minus 1/4 G squared F ABC F A B prime C prime, and then 4 gluon A mu B, A mu C, A mu B prime, A mu C. So the interactions of QCD are contained in those last 3 lines. These are what give you directly the Feynman rules of QCD. I'll skip writing down the free vertices and just go directly to the interacting ones. This structure is completely analogous to the same vertex in QED. In QED, the Feynman rule had draw it this way. You had a photon and an interaction with an electron-positron pair, and this vertex was minus IE gamma mu, where mu was that vector index for QED. The only thing that's different is that now, in addition to this gamma matrix that shows up in between psi and psi bar, I also have the color matrix TA. And then I also have a trivial change in convention where I call the coupling constant plus G instead of minus. So if I make this a gluon in QCD that has vector index mu and color index A, then the corresponding vertex is plus IG gamma mu times TA. The much more interesting ones are these two. These have no analog in QED. These are contained completely from gluons. So this first vertex involves 1, 2, 3 gluon fields interacting with each other. Notice, however, that this vertex is not democratic in which field is which. 2 of the fields are just standing there, but the last one, the third one, has a derivative on it. A derivative in position space becomes a factor of momentum in Fourier space. So when I write down this expression, I'm going to have something that involves the coupling, I'm going to have some kind of FABCs in it, and the vector index, the mu, is going to come from the K mu's of each of those gluon lines in all possible combinations. So I'll show this Feynman rule for you in a second. I'm not going to bother writing down all of the tree of indices here to get it all right. But notice that it has this derivative coupling. In order to get the vector mu, you have to get it from the momentum, because there isn't a gamma mu to give it to you instead. This last term is really interesting. This is a 4 gluon vertex. Which honestly, I can't say I've had a real occasion to do very much with in my career. Most all of the physics effects that I work with in practice are coming from the 3 gluon vertex. But I guess if you do a high enough order calculation, then all of the full structure of this 4 gluon vertex should show up. This one is not so painful. There's no derivative coupling. So all the mu's and the nu's that show up will show up in the form of tensor mu's. So you'll have G squared that goes into this. You'll have color combinations. And all of your tensor structures will show up in the form G mu nu, G alpha beta, and so on. So to show you the structure explicitly, let me jump to the notes. Oh, recompile. Sorry, I guess this part would have been faster if I had a separate PDF. Okay. Here we go. So here with all of the conventions specified are the 3 and 4 gluon vertices in QCD. Here, if I have all 3 momenta coming in, K1, K2, K3, all directed inward, then there's a particular cyclic pattern or symmetry to those indices 1, 2, and 3. Notice that it comes in with the momentum dependence, and because of the symmetry, it comes in actually as a difference of momentum. So here you get the Lorentz index of particle number 3 and the difference in momenta of particles 1 and 2, plus all cyclic permutations of that structure. Whereas the 4 gluon vertex comes in at order G squared. It has funny color combinations, and the mu nu structure is all in terms of G. I guess maybe rather than letting me go back to the blackboard, I can sort of point now to the next steps of the implications. Once you've built the theory for QCD, you can calculate all of the renormalization, all of the one loop properties exactly the same way that you do in QED. But you find that these new vertices that you've added fundamentally change the implications of the theory. So when you calculate in particular the running coupling, you calculate the vacuum polarization, which is responsible for port identities. You have not only the first diagram, which is the diagram that you have for QED. In QED, you have photons that fluctuate into particle-antiparticle pairs that act like a dielectric. You have positive negative charges that fill up empty space, and they absorb some of the that goes into the field that effectively polarizes the vacuum. So this is what you calculate to get the screening of the electromagnetic field in QED due to vacuum self-interactions. In QCD, you have the same thing, but you also now have a new contribution coming from self-interactions of the gluons. And the thing that's so remarkable is that the self-interactions of the gluons come in with an opposite sign. So they actually compete against the effect of the fermions, the quarks. So if the fermions act like a dielectric, they sort of fill up the vacuum with positive negative charge pairs that decrease the strength of the electric field as you go over further distances. Gluons are trying to do the opposite. They act like a para-electric or a paramagnet that increases the strength of the electromagnetic fields as a function of distance. So when you calculate the running coupling, the vacuum polarization, you have a difficult fight between the two effects. And it's not obvious who's supposed to win. The answer to that competition depends very delicately on the number of colors in your theory versus the number of flavors in your theory. The more flavors you have, the more quark loops, and therefore the more dielectric effects of the vacuum. The more colors you have, the more gluons there are, and the more para-electric effects. So depending on what regime of the theory you're in, you could get either positive or negative values of the beta function. But for QCD as we know it, with NC equals 3 and only a handful of quark flavors, the gluons win. And that negative term in the beta function that comes from the gluon self-interactions totally turns over the behavior of the self-interactions in QCD. So that instead of having a running coupling that gets smaller as you go to lower energies and bigger as you go to higher energies, QCD does exactly the opposite. So if I put this plot here for QCD side by side with the same one for quantum electrodynamics, the curves look exactly opposite. I think I can annotate my own. Yes. So for QED, the behavior is exactly the opposite. It grows as you go to high energies. But for QCD, because of these gluon self-interactions that completely change the direction of the running coupling, in QCD, it runs the other way. So in QCD, the coupling gets weak at high energies or large momentum transfer, short distances. That phenomenon is called asymptotic freedom. It means that QCD is weakly interacting deep inside the proton wave function. If you measure it in deep inelastic scattering at very, very high Q squared. But conversely, it means that QCD is very strongly interacting at low energies and low momentum transfer scales, or long distances, where long means long compared to 1 femtometer. So the paradox of QCD is that it is weakly coupled at short distances so that we can calculate exactly what's happening to individual quarks and gluons in a hard scattering. But I can never calculate the proton wave function. And if somebody tells you they can calculate the proton wave function, you should be deeply skeptical, because the proton wave function is a non-perturbative quantity that happens exactly where alpha S is its largest, and you do not have the ability to describe the dynamics in terms of quarks and gluons. Now, maybe it's an accident, but I find it quite telling that both in the QED case and the QCD case, that the reason the coupling is blowing up the way that it does is related to a phase transition. In QED, when the coupling is doing this, it's blowing up as you go to high Q squared. Eventually, the coupling diverges to infinity when you get to the Landau. And it's perhaps not an accident that that explosion of the QED coupling at high momenta shows that a breakdown occurs exactly where QED becomes the wrong theory. At high energies, at high momentum transfer, there is an electroweak phase transition where QED goes away and it changes, it unifies together with the weak force to have very different properties above that phase transition scale. So perhaps I'm reading too much into it, but when I look at the Landau pole of QED that blows up like this, and I see the electroweak phase transition here, I can't help but notice that there's a mirror counterpart to what QCD does the other way. When the coupling blows up in the infrared, that is indicative that there is a chiral phase transition that happens in QCD at low momentum. The essential difference is that in QED, the phase transition is at high scales, and the theory is well behaved at low scales. QCD flips that on its head, so that in QCD, the difficult phase transition is all at low scales. All the hard problems are about protons and neutrons and low energy physics. But the thing which is the greatest virtue of QCD is that it is self-consistent. It is well defined up to arbitrarily high energies. That is the essential virtue of the running coupling, that because the coupling goes to zero, my theory becomes simple in the limit of infinitely high energies. And that is the angle that I want to take going forward for the discussion of small x and high energy Eichenal scattering. So in my mind, the thing which is most profound about QCD is that QCD is perhaps our only template. I'll put only in quotes because I can't rigorously defend it. For a UV complete theory of nature. UV complete means that my Lagrangian, my theory, is perfectly good to go all the way up to Q squared going to infinity. It's valid no matter what energy scales I want to go to in terms of energy, momentum transfer. That the UV limit is completely well defined and safe, stable. So the theory is UV complete in the sense that it does not break at high scales. That is the opposite of what happens in QED. QED is not an acceptable fundamental theory of nature at infinitely high energies because QCD blows up at infinitely high energies. The true theory of nature, whatever it is, whatever grand unified theory we have, is a well-defined theory up to infinitely high scales. And that's what's so compelling about QCD is that QCD is perhaps our first candidate for what a UV complete theory of nature can look like. QCD handles it by asymptotic freedom. It's that beautiful property that alpha S of Q squared going to infinity means alpha S goes to zero. And it's that weak coupling that makes it also tractable at very high Q squared. This is where we would like the story to stop so that we can, I don't know, appreciate the beauty of QCD and sing kumbaya about how wonderful it is that we have a UV complete template for a theory of nature. But the problem is that this elegant solution that gives us something that is UV complete on one hand, at the same time poses a fundamental challenge to that idea of UV completeness. But the exact same non-abelian gauge theory, the non-abelian nature of QCD leads to an explosion of density. That threatens to violate unitarity. At high energies. So when I say, hooray, QCD is a UV complete theory of nature, if I really dig into the details, I have to pause and say, or is it really? Have I really demonstrated that it is an effective UV complete theory of nature? It may be UV complete in the sense of the coupling gets weak and I can calculate it, but if that also leads to a violation of something like unitarity, then my theory is broken for a different reason. This effect is what leads us on the road towards gluon saturation. We say this effect leads to a whole lot of gluon Bremsstrahlung, and that gluon Bremsstrahlung leads to even more gluon Bremsstrahlung. And I get a cascade of gluons radiating more and more and more gluons at high energies. That essentially leads to scattering probabilities that get higher and higher and higher as your target gets more and more opaque. If I don't do anything about it, I'm going to get nonsense. I'm going to get probabilities that blow up so fast they get bigger than 1. In order to save my theory, I have to preserve unitarity. And that means I cannot let this density blow up as much as it wants. There must be nonlinear interactions that regulate that growth of the gluon density to make it well-behaved and unitary at very high energies. So this is the angle that I want to pose the discussion about small x physics for in the next lecture or so. When we calculate quark-quark scattering and quark-quark scattering plus gluon radiation, and we get that leading log kernel that shows us that there's an enhancement of that gluon density, I always bring it back to the cause of all of this is the non-abelian nature of QCD. And we need to understand this because this is an essential feature of how QCD is a UV complete theory of nature. And if we understand this about how QCD unitarizes itself to maintain its well-defined properties even at infinitely high scales, then we'll learn something about how UV complete quantum field theory should behave. We'll learn something about candidate fundamental theories of nature. So I am not a particle physicist. I don't know anything about fundamental particle theories beyond what I learned in Peskin. But what I do know is that it's not an accident that one of the candidate theories of particle physics is Technicolor. If you haven't heard of it, Technicolor is a modern version of QCD that basically says, what if things that look like fundamental particles to us now, like, I don't know, the electron or the up quark, what if they, like the proton, are not fundamental particles, but they're bound states in some force that looks a lot like QCD, that is asymptotically free. It has some new color dimension that's different from QCD color, so they call it Technicolor. But it's just a copy of QCD. It's the idea that I can take this non-abelian asymptotically free theory and I can massage it in different ways to try and get versions of UV complete theory of nature. I don't know anything about Technicolor, but I guarantee you Technicolor suffers from this problem because Technicolor is an asymptotically free non-abelian gauge. And this automatically leads to this in ways that we will discuss in the next couple of lectures. So maybe let me pause here. The next thing that I have in my lecture notes is a calculation of quark-quark scattering and then quark-quark plus glue. So we'll actually take this Lagrangian, we'll roll up the sleeves and calculate some amplitudes and cross sections together, and then discuss the implications of that and how that leads us ultimately to gluon saturation. So yes, maybe I'll stop here. What questions or comments do you have?
Can I ask a question?
Yes, please.
So thinking about this violation of unitarity, is this only in the limit as Q goes to infinity, or is there some finite energy scale where our S matrix just goes from being unitary to not?
I think the answer is that if you do not have the nonlinear effects that slow down the density, basically you're in a regime where the gluon density, let's say density rho as a function of energy, it starts to explode very quickly. At low energies or low densities, you have that exponential growth, so to speak. But then when the density gets sufficiently high, instead of continuing to blow up, this thing slows down and asymptotically saturates. That's more or less what we're talking about. So I can define the point at which the sort of exponential growth now is total nonsense. There is a point where I have 100% probability and my linear extrapolation just crosses. But in the solved theory, it doesn't cross, it sort of smoothly slows down and asymptotically approaches that maximum value. Really, the more technical way to describe what I'm talking about here is as the Wilson line, the trace of two Wilson lines, the two of a dipole. So I'm not sure if I've answered the question. It is possible to say, where is the linear regime irredeemably broken? It's a much more subtle question to say, where did the nonlinear effects turn on? It's not a hard number, right? You could say it's here, you could say it's here, you could say it's here. Really, there's sort of a continuous region where that change is occurring. Does that make sense?
Yes, that answers it perfectly, thanks.
Okay, great.
I have a question.
Yes, please.
I want to ask why does QCD being non-abelian make it so interesting? Is it the fact that we can now have these multiple degrees of rotation?
Yeah, so I mean, I'll tell you why it makes QCD so interesting to me, but that's perhaps a biased answer. I'm interested in the physics of QCD at high energies. And the answer essentially of what I'm going to derive for you in the next couple of classes is that if you have high energy scattering, imagine I've got QED for a second. So I have an electron and it scatters off of another electron. And in the process, it radiates a photon. So this would be an example of the amplitude for very high energy electron-electron scattering. And you ask yourself, what is the total amount of intensity or the total amount of power that gets radiated in photons? In the limit, let's say S goes to infinity. This is that forward scattering limit that I described before, where C is held constant, and therefore the scattering angle is small. It's going to zero. You can calculate this in QED just fine. And the answer that you get in this limit, remarkably, is 0. The sigma equals 0. And the reason is very simple. At the amplitude level, this diagram and this diagram in the limit S going to infinity are basically the same thing. And they come with a minus sign. So at the amplitude level, I have one interference pattern from initial state radiation that gets exactly canceled by a pattern from final state radiation. And that makes perfect sense physically, because we know what it takes to make charged particles radiate power. In classical E&M, to make a charged particle radiate, you have to accelerate, you have to shake it. And if I have infinitely high energy scattering, where the scattering angle is theta equals 0, then the electrons don't accelerate. They go right through each other with 0 deflection angle and basically no change at all. So it makes perfect sense that for an abelian theory, that there is zero power radiated. And the reason for zero power is the kinematics of this amplitude and the kinematics of that amplitude are identical, and they just cancel each other with minus. What happens in QCD? The exact same thing with only one change. And that one change is now if these are gluons, now I have matrices, TA and TB. And now here I have TB and TA. And now for QCD, instead of getting 0, I get TA, TB minus TB, TA, which is precisely the commutator. And this is not 0 because QCD is a non-abelian theory. It is instead equal to IFABCTC. So for me, the reason QCD is so profoundly interesting, especially at high energies, is because QCD radiates like crazy. QCD has all kinds of dynamics at high energy that QED does not. Because, as you say, QCD has internal directions that it can rotate in. So the language that I would use for this is that kinematically, they're not accelerating. The deflection angle is 0. But if I have exactly the same process for quarks, I might have a red quark coming in and a blue quark coming in. And even if they go straight through each other, my red quark could become a green quark, and my blue quark could become a red quark. So they can accelerate in color space, quote unquote, even though they are not accelerating in angle. The effect is the same. When you calculate it in QCD, that difference in colors, the acceleration in color space, leads to a non-zero answer. And this has profound implications. So I would say the short answer is QCD is so damn interesting because QCD radiates huge amounts of gluons at high energies, and QED does not. They are fundamentally different. The high energy limit of QED is simple. The high energy limit of QCD is fascinating. Does that answer the question?
Yes, that was a really good answer. Thank you.
Great, thank you.
More questions?
All right, well, if not, then thank you guys very much. And we will pick up with this tomorrow and calculate some scattering analysis.
Thanks again.